In this lesson, we will look at an introduction to the properties of gases. Gases are described by a theory in chemistry and physics known as the kinetic molecular theory. And what the kinetic molecular theory does is describe something known as an ideal gas. According to kinetic molecular theory, gases are all composed of small particles. This is nothing new. We're already considering matter to be composed of small particles, which could be either atoms and or molecules. An unusual part of kinetic molecular theory is that we consider particles to be something called point sources, meaning that they have no volume themselves. That's reasonable when we consider that for a sample of gas occupying a container, the volume of the particles compared to the total volume of the gas tends to be negligible, meaning that we can neglect, while it's in the gaseous state at least, we can neglect the volume of the particles. The particles of a gas are in constant motion, meaning that they have kinetic energy, and that motion has some consequences that we can measure. We're going to look at measurable variables in a moment. But some of the measurable variables, such as pressure, for instance, are due to the particles being in constant motion. We consider the particles to have no attractive forces between them, or repulsive forces. The lack of force is evident in the fact that the gas particles stay separated. They don't tend to condense together when we're considering them to be a gas. However, there actually are attractive forces. For the ideal gas, we consider them to be negligible, just like we considered the volume of the particles to be negligible. We also consider that due to the lack of attractive forces between particles and their container, the particles have what's known as perfectly elastic collisions. Perfectly elastic collisions means no loss of kinetic energy during a collision. No loss of Ke during collisions. And we can say that the kinetic energy that they have is proportional to Kelvin temperature. And we're not going to bother with the equation in this particular course that relates kinetic energy of the particles to the Kelvin temperature. However, there is one, and we make it proportional to Kelvin for a reason, and you'll soon see the reason for that as we get into some of the mathematical description of gases. So any gas that obeys all the postulates of the kinetic theory are known as ideal gases. And most gases resemble ideal gases within certain temperature ranges. And pressure ranges. That would be high temperature and low pressure. And we will talk about both temperature and pressure in the coming slides. So most gases, for instance, room temperature oxygen in the room that you're in right now behaves very much like an ideal gas. The same would be true of nitrogen. Some other materials at room temperature may not, such as water vapor, for instance. So we said that we have measurable consequences due to the motion of particles, and we're going to look at some of the variables that are often used to describe gases. First is going to be volume. Volume, as we already know, is the amount of space occupied by a gas or anything. The SI unit for volume is the cubic meter. This is a very large unit and very rarely used in a chemistry lab. So others include cubic decimeter, liter, cubic centimeter, and milliliter. You need to be able to convert between these, and just to review the conversion factor that I gave you earlier in the semester, 1 decimeter cubed is equivalent to 1 liter, which is equivalent to 1,000 cubic centimeters, which is equivalent to 1,000 milliliters. Looking at this conversion factor, we can say that centimeters cubed are equivalent to milliliters, and decimeter cubed are equivalent to liters. All of these are commonly used, and it's important as you solve problems to check the units to make sure that you're using the appropriate one for the problem. Another measurable variable is temperature. SI unit for temperature is the Kelvin unit. Others include Celsius. Here's our relationship that we use to convert between Kelvin and Celsius. You've seen this numerous times. It amounts to just taking the Celsius temperature and adding 273 to it, if you want a quick conversion. Temperatures that we use most often are in Celsius. So in a lab, we'll tend to use Celsius temperatures, but to be able to be used mathematically, they have to be converted to Kelvin first. And again, we'll talk about why when we get to the actual math. We have something known as standard temperature, which is 273 Kelvin, or 0 degrees Celsius. Standard temperature is a temp for comparison. There are other standard temperatures in chemistry, but for gases, this is the one that we use, which is a little bit cold maybe for a standard lab scenario, but nevertheless we use 273 Kelvin as the standard temperature. Next comes pressure. Pressure is defined as the amount of force per area. The SI unit of force is the Newton. SI unit per area is the square meter. So the SI unit for pressure is the Newton per square meter, which is known as the Pascal unit. Since a Newton is not really a lot of force, this is a rather small quantity in terms of pressure. So standard pressure, which is again a reference pressure, is a rather large quantity, 101,325 pascals. When we have, now that we have reference or standard pressure and standard temperature, we can combine those and call a condition known as STP, standard temperature and pressure, 273 Kelvin, 101,325 pascals. So when we describe a gas, very often we're describing it either in standard temperature and pressure or some other temperature and pressure that relates back to STP. If you see STP in a problem, that means that we have two conditions given. This is not often the unit that's used, even though it is the SI. Other units include the atmosphere, and these are all given at standard, meaning that these are all equivalent pressures to 101,325 pascals. So we have 1 atmosphere of pressure. Kilopascals is most often the version of the Pascal unit that we use, and that's 101.325, or more often 101.3 kilopascals pressure. And so that would be the 4 significant figures. 760 torr. The torr, named after an Italian physicist, Torricelli, or the Torricelli units, are also known as millimeters mercury. We'll see why we can use a distance for a substance when we start talking about measuring pressure. And then we want to think about what is the source of pressure. If we've got a balloon that's blowing up and we have gas inside, and then you reach out and squeeze the balloon, so you apply a force from the outside, you can feel the balloon pushing back. That's what we mean by pressure. So what is the source of this pressure? Well, we know that these particles are in constant motion. And when they're in constant motion, they collide with each other, but they also collide with the walls of the container. So the source of the force that's applied to an area, the source of the force, is considered to come from collisions of particles with wall of container. Or if we talk about pressure, period, we would say that pressure is due to collisions of particles with whatever surface. So if the atmosphere is applying a pressure to your eardrum, and the atmosphere is a gas, then the pressure is due to collisions of the gases in the atmosphere with your eardrum, or your skin, or the surface of a body of water like a lake or the ocean. So pressure, again, from collisions of particles with walls of the container. Now, to measure pressure, we use something known as a manometer. There are a couple of types of manometers, open and closed. This is a closed-end manometer. That means that this side is closed. We have a gas container over here, a valve on this particular one at least, and inside we have liquid mercury. Okay, and at this point there is no gas on this side, so we say that we have 0 atmospheres or 0 pressure, approximating that. And on this side we always have, in the closed-end manometer, we have a vacuum. So in this sense we've got a vacuum versus a vacuum, and you can see that the levels of mercury are the same. The amount of force applied to this side is equivalent to the amount of force applied to this side. So if we look at another scenario, where in this case we've got a gas with a pressure of 1 atmosphere inside the container, the valve is open, and that allows gas to flow through, being a fluid, until it applies a force, where the pressure of the gas is applied, the force of the gas is applied over the surface area of the mercury inside the column, and that gives you the pressure of the gas on this side. On this side, the vacuum, which has a pressure approximating 0 atmospheres on this side, the pressure is 0 essentially, so this gas is pushing up against nothing. And what's going to happen is that it's going to raise the mercury by allowing the mercury, Hg, to flow until the height difference is equal to its weight. So at the point that the gas is applying a pressure, or an amount of force, and the amount of force is going to be equal to the weight of this column of mercury over here. So the end result is that we can say, if we look at the difference, maybe this is 760 millimeters on this side, then we could say that the pressure of the gas equals height difference of Hg in the manometer arms. Okay, so if that's 760 millimeters, then the pressure of the gas is 760 millimeters, which is equivalent to 1 atmosphere. That's the reason I chose that number. Now we also have another type of manometer, which is probably a little bit easier to produce, and that is the open-end manometer. In this end, the atmosphere is available on this side rather than a vacuum, and then we've got the gas over on this side. Again, we open the valve, and the gas flows until it applies a pressure on this side. If the atmosphere is applying a pressure over here, we basically have atmosphere versus the gas. And in this case, we can see that the levels are equal, so we can assume that the atmospheric pressure and the gas pressure must be the same. To be able to use this, we need to be able to measure atmospheric pressure. If the mercury level is higher on the atmosphere side, so mercury higher here, gas pressure higher than atmospheric. If the mercury level is higher on this side, that means the atmosphere is pushing down, so higher here, atmospheric pressure higher. So when we look at this, so let's imagine that we have this scenario where I'm going to mark out this. So let's imagine we don't know that. And we've got, let's say that we've got an atmospheric pressure pushing here, and let's say that that is 1 atmosphere. So if we have 1 atmosphere pressure here, and we have a height difference of 760 millimeters, which is also 1 atmosphere, then we would say the pressure of the gas equals the pressure of the atmosphere plus the difference in height of mercury. So this is going to be 1 atmosphere plus 1 atmosphere equals 2 atmospheres for the gas. So let's look at a barometer. A barometer is a type of closed manometer. Get my pen back. So barometer is actually a unique special type of closed end manometer. That's because at the top end up here it's actually going to be sealed so that there's a vacuum there. So if you can imagine the sealed tube is then immersed into a pool of mercury. This is mercury down here. And the mercury will rise up the open tube or the closed-end tube against the vacuum until it reaches a certain point. At the point that it reaches its height, the force to lift the mercury column equals its weight. So the force to lift is going to be an upward force. The weight is going to be a downward force. So they become equal, and the mercury stops rising. So what's actually doing, what's supplying the force? It actually is the atmosphere pushing on the surface of the mercury here. So here, mercury pushing, or atmosphere pushing down. There's nothing inside the tube pushing down because we have vacuum. So the end result is that the mercury rises up the tube, and the atmosphere is basically atmosphere lifts the mercury. And at the point that the force that can be exerted by the atmosphere equals its weight, which is gravity pulling the mercury back down, the mercury will stop rising. On a daily basis, the amount of lift in the atmosphere depends upon the atmospheric pressure. So if a high pressure system is riding through, then we may be at this point. But if a low pressure area moves through, a stormy day, then we might find that the mercury level drops. But gravity, or the weight of the mercury, is going to be the same regardless, because the barometer would be generally mounted in a room somewhere, and gravity is not going to change in a particular room. So anyway, what we actually look at, and you can't see it on this particular tube, but there would be some sort of rule or measurement ruler back here, and marked in millimeters or inches or centimeters. And the end result is that we would have, we would measure the height of the mercury column that could be lifted by the atmosphere. On an average day, we get standard atmospheric pressure at sea level, and that would be 760 millimeters worth of height. So the barometer measures the atmosphere, and it's also necessary to measure a gas with a open-end manometer, because you have to know the atmospheric pressure. We're going to stop the presentation at this point. The next one we'll look at some of the mathematical relationships between the variables and the gases.